Okay, so here we are doing another example, and we're asked to find the equation of the tangent line to this curve at the point 2, 1. So we will start off by taking the derivative of both sides of the equation. So I'm going to use just the prime notation instead of the Leibniz notation in this problem. So one thing I'll point out is that if you want to write that you are taking the derivative of this entire thing, you can put it in parentheses and put a prime. Just make sure that this is really clear. You make it big enough that it's visible, right? And then you can write this like this. Although it's not ideal, it's kind of strange notation, but it's understandable. Okay, so this is going to be, okay, let's start with the left-hand side. 2x is the derivative of x squared, so we just start off with that. And then x times y requires the product rule. So we get 1 for the derivative of x times y plus x times the derivative of y, which is y prime. And then on y squared, we use the chain rule. So that would be 2y, that's the derivative of the outside function, times y prime, the derivative of the inside function. And then derivative of 1 is just 0. Okay, so I'm going to first distribute this negative, and then we will solve for y prime. Equals 0. So we have two terms with y prime in them, this one and this one, so we'll move the other terms to the other side of the equation, and we will get negative x y prime minus 2y y prime equals y plus or minus 2x. And then we can factor that y prime out of both terms, and we'll be left with negative 2x minus 2y. And then to get y prime by itself, we just divide by that expression. So we'll get y minus 2x over negative x minus 2y. Okay? And then we want to actually evaluate this at the point 2, 1. So remember, this is, well, I'll just write it here. So that means x is equal to 2, y is equal to 1, right? So just plugging that in, that means our slope is going to be, we'll plug in the points. So 1 minus 2 times 2 over negative 1 minus 2 times 1. Oops, this is a 2, negative 2. Okay. Now simplifying, we get negative 3 in the numerator and negative 4 in the denominator, so 3/4 is going to be our slope. And we are already given the point, right? So if the tangent line is tangent to the curve at this point, then that point lies on the line. I'm just going to move this over. Brought a y with me. Okay. Try and put it back. Okay. So we have the slope, we have the point, we just need to use our point slope form. So the tangent line will be y minus y1, which is 1, equals the slope 3/4 times x minus x1, so minus 2. And if we want to write this in the standard form, we can just move this over. 3/4 times negative 2 is negative 3/2, right? Yeah. And then we add 1, so this would be minus 1/2. Okay, so that would be our answer for that problem. Okay, So there's one more thing I wanted to do, which is talk about derivatives of inverse trig functions. So we did introduce the notion of inverse trig functions a while back, and we can actually find their derivatives using implicit differentiation. And so what we're going to do is remember how these trig functions were defined. So they were defined as the inverse, so we'll start with sine. So inverse sine was defined by this relation. So sine inverse of x equals y if and only if sine of y equals x. And this is just what it means for this function to be the inverse of sine, right? That's just the definition. And the domain was, this is for y between minus pi over 2 and pi over 2, right? So we had to restrict the domain in this case. Now, what we can do is take this equation that relates x and y and use implicit differentiation on it. So I'm going to use implicit differentiation. Okay, so that means we take the derivative of both sides. So I'm going to write that down. So first the derivative of sine of y, and then the derivative of x. Now the derivative of x is just equal to 1. The derivative of sine of y, remembering that y is a function of x, we have to use a chain rule, right? So we would first get cosine of y, and then we would get, we can use the y prime notation for that. And then it's not so bad to see that this is just equal to 1 over cosine of y, right? Okay, but that is the definition of the derivative in terms of the function itself, and that seems a little strange. And we can actually solve for it to figure out what this would be in terms of x, which is what we would want, right? We want to have our definition of the derivative in terms of x if we possibly can. And since we know that inverse sine of x is actually a function when we restrict the domain in this way, we should be able to do that. Okay, so how we can do that is first to notice that cosine of y is greater than or equal to greater than or equal to 0 on this interval that we've restricted our attention to. So this is minus pi over 2 to pi over 2. And you can see this by just looking at the graph. So if you remember that cosine is the one that starts at 1 and then goes off like this, and then we know that the function's periodic, so it looks the same in the other direction as well, right? And this point where it hits 0 is pi over 2, and then since it's symmetric about the y-axis, this is minus pi over 2, right? So you can see just from the graph that this function lies above the x-axis on that portion, right? So we know that if y is between minus pi over 2 and pi over 2, then cosine of y is greater than or equal to 0. And that will come in a second. So, so this is just off to the side. And then what we're going to do is write cosine of y as the square root of cosine squared of y. So all we've done is take this function, square it, and then take the square root. And hopefully you remember that when we do that, when we take a function, square it, and take the square root, what we get is the absolute value of that. So if we take a number, square it, and then take the square root, we get the absolute value of that number. So you could check, say, with minus 2, if we square that and take the square root, we get the square root of 4, which is 2. So when we put in a negative number, we get out a positive number. When we put in a positive number, we get out a positive number that matches in magnitude. Okay. So I can write this way, and we know that these are equal because cosine of y is always positive on the domain. Okay, so then I can now replace this with 1 minus sine squared of y, and that is from the trig identity. That's cosine squared y plus sine squared y equals 1, right? So we're just using that. And then we know that sine squared of y, we have a formula for that. So that's just equal to x, right? That means that we get 1 minus x squared by just replacing that. And so we can rewrite y prime as 1 over this expression. So now we found an expression of cosine of y in terms of x, and so we can just replace it with that. 1 minus x squared. So square root of 1 minus x squared. And this is the derivative. So I'm actually going to rewrite this. So, okay, so in conclusion, the derivative of inverse sine of x is equal to 1 over square root of 1 minus x squared. Okay? And then the derivatives of the other inverse trig functions will go similarly, and you may see some of that on the in-class work. But don't forget to complete the comprehension check question.